Perfect.
Yeah, so welcome everybody to the Building Cost-Efficient Serverless Applications webinar. My name is Tavi, and I am the CEO and founder of Dashbird. First of all, this webinar will be recorded, and you can later look at the recording. You can also ask questions and comment in the webinar chat or Q&A functions in Zoom. There's a chat button and the QA button down below. So feel free to do that, and we will answer your questions either in the chat or later there will be a Q&A session in the webinar as well. So we will address questions through the video as well. Before we start and before Renato starts going through the presentation, I'm gonna just give a quick introduction into why we think we are competent in speaking about cost optimizations and kind of our background in serverless. So Dashbird was started by developers building serverless applications. We've built multiple large-scale serverless architectures based on Lambda Functions and other managed infrastructure in AWS. That's why we started Dashbird, to solve and address some of the challenges that developers are facing when they're going into modern cloud development. We're a monitoring platform. We offer data centralization and democratizing the data for compute resources. We also have an incident management and detection platform, or a feature that basically detects any kind of failures from your architecture, and also a continuous insights engine that looks over your AWS resources and lets you know if something is not right. And we're currently used by over 7,000 AWS environments. And yeah, basically hoping to provide value and help companies succeed with serverless. So over to you, Renato. You're muted.
Okay, so my name is Renato. I'm a developer advocate at Dashbird. I've worked for several years building several different systems on top of serverless services for backend APIs, machine learning projects, basically everything. A little bit about my personal background. I'm also married. I'm a father of two. One of my kids are not born yet. Well, the pregnancy is due for August. I live in the woods. I enjoy spending time with my family and very close to nature. And yeah, so I'm a big serverless enthusiast. I'm a Dashbird enthusiast. I was actually a customer of the company in the past, and I enjoyed the service so much that I decided to join the team to help them move forward with this platform. Let me just make one very quick adjustment here on my setup, guys. Just 1 second. Yes, I have to change the presentation mode. All right. Okay, so can you see the slides again?
Yeah.
Yeah,
it's
okay.
Perfect. Okay, now we see the presenter view actually. So before it was excellent.
Okay,
but now
let me close this one then.
Yeah.
All right. So we're going to be covering these 4 optimization areas. It's going to take about 20 minutes. We'll go through how to optimize API endpoints, Lambda functions, databases, and a little bit about caching strategies for those 3 previous topics. And at the end of the webinar, we're going to have a Q&A session. So as Tavi said, you can send your questions either in the chat or the Q&A channels of the Zoom interface, and we're going to address those questions at the end. And the motivation for this webinar was one of the pillars of the well-architected framework by AWS is the cost optimization pillar. So it basically guides us through 4 different areas that we need to be aware of in order to have cost-effective cloud architectures. It's obviously choosing the most cost-effective resources for the jobs that we need to get done, matching supply with demand, so making sure those resources have enough capacity to meet demand, but not more than is really required, which would lead to waste. Being aware about where our money is going in terms of our AWS bill, what is costing more, and which areas are growing in cost. So those are important things for us to monitor, and keep optimizing over time, keep monitoring the architecture. So it's somewhat a moving target, so it requires a constant basis analysis. So starting with the API endpoints, the first area that we would like to share with you is about maybe replacing an API gateway with an application load balancer, because API gateways are awesome, but it can be a little bit expensive in some, maybe cost prohibitive in some cases. And the ALB also integrates with Lambda Functions as seamlessly as an API gateway. It's also highly available. It can scale to hundreds of thousands of requests per second, even millions of requests if you warm it up appropriately. And it's potentially cheaper, a lot cheaper for high throughput APIs, as we're going to see. So we draw a hypothetical scenario for an API that's available 24/7. It receives around 5 million requests per day, averaging 60 requests per second, and having peaks of 120 requests per second at some points of the day. The request response payload size averages around 1 kilobyte each. And there are basically 10 rules for request routing being processed by this API. So the math is, for the REST API, it's going to cost around $500 per month. The HTTP API, which is the new version, the simplified version that AWS launched last year and went generally available recently this year, would already save a lot of money, reducing to $150 per month. But if we consider an ALB for this exact same use case, it can save us even more money, even in comparison to the HTTP API, reducing to around $60 US per month. So for high throughput APIs, we can see that ALB is a very good opportunity for cost savings. And if we do need to stay with API gateways for whatever reason, let's say ALB is not really a good solution for us, for, I don't know, maybe there's a feature that's missing there and we need the API gateway one, maybe the HTTP API could be a good solution, especially for internal workloads. It's 3 times cheaper than the REST API, and it's a good alternative to decouple Lambda functions, for example, instead of having multiple Lambda functions calling each other in a highly coupled way. We could use the API gateway HTTP version, which is a lot cheaper to decouple those Lambda requests. And the features that are missing are not really very important for most internal use cases, especially. So it wouldn't be worth paying extra for the REST API to have SDK generation or usage plans or a firewall, for example. If it's used on internally, we don't really need these public security features for firewall, for example. The concurrency and throttling features that the REST API provide are very cool, because we can set throttling per client on a client basis. But on the HTTP API, we miss this feature, but we still can control concurrency on the Lambda level. So for internal purposes, that might be more than enough. And in terms of authentication and authorization of requests, the REST API is much richer. It has much rich features, but we can use JSON Web Tokens, which is an open standard. It's very easy for developers to work with in the HTTP API, so it might be enough for our internal use cases as well. And a little bit about caching. The API gateway offers caching possibilities for us. We can apply caching on the API level or on a per method basis only for those methods that can support cached responses. Some of them may require the most up-to-date information, so they wouldn't be suitable for having a cache in front of them. We can customize the time to live for each method or for each API, for example, to suit our needs. And the downside of the API gateway cache is that AWS charges us on an hourly basis for the cache size that's allocated, not for the actual usage. So we need to benchmark against our use case, because if our requests, if the types of requests that are hitting our API is quite variable, it's much less likely that the cache is actually going to be used. So in this case, the cost opportunity savings are much lower. But if we get a lot of requests that are identical to each other throughout the day, the cache might reduce a lot of downstream requests from the API gateway. So instead of the API having to forward requests to a Lambda function, for example, to execute a bunch of stuff, you can stop on the API and respond to the client immediately from the cache, and actually reduce latency and reduce costs on the downstream requests that the API would have to generate. So it really depends on each use case. We really need to benchmark against our usage to see if the cache is really going to save money or not. Moving now to Lambda functions. It's a little bit obvious, but it's not. It doesn't hurt to remember that it's important for us to prioritize what's taking more money from our pockets. So it's very common for development teams to have, I don't know, hundreds, even thousands of Lambda functions. So it can be a daunting task and very time-consuming to work on optimizations for all of them. And for Lambdas that are really costing, I don't know, a few dozen bucks, even 100, 200 bucks a month, it may not be worth the time of a developer going through this function to identify any possibilities to save money, because just the development time will cost more than any possibilities to save on the cloud bill. So we need to focus on where there is a greater opportunity to reduce costs. AWS provides this data for us, but it's not quite easy to extract the data in a way that's fast for us to digest. So there are services like Dashbird that provides us this very quickly out of the box, so we can browse all of our Lambda functions, for example, in Dashbird, and quickly see how much each of them are costing us. You can rank order Lambda functions by the number of invocations, which are the ones that are probably driving the higher costs. So it's very easy for us to go through these cost optimizations in a more prioritized way. Another way for us to save money is to benchmark which is the optimal Lambda memory setting for each of our functions, because AWS allows us to customize the memory, but it doesn't give us any customization options for CPU. So what they do is, the more memory we allocate, the more CPU we get. And the more CPU we get, the faster our code will execute, which leads to shorter build duration and a lower build. So it can actually, the higher memory will cost more per millisecond, but it can actually make the code faster and offset this cost and render an effective saving at the end of the invocation. There is one caveat to these strategies. One of them is, there are a few caveats actually. You can actually read more on those two articles. We're going to share the slides after the webinar by email. So you can go through the slides and click on these links here and read those two articles we published recently with more details about the strategy. But one of them, perhaps the most important one, is that above 2 gigabytes of memory, AWS is actually going to split the CPU power in a second vCPU. So for single-threaded workloads, you're not going to see any speed gains by increasing memory above 2 gigabytes. So you will only spend more money on more memory allocated and not get any cost savings. So here is just a quick example. We have this GitHub repo here. We published a benchmarker function that you can plug to any Lambda function in your AWS account to benchmark. It just generates a bunch of requests and keeps changing the memory setting of your Lambda function to test how long it takes to process your requests on different memory settings. And it also contains a sample Fibonacci function. It's just a CPU-intensive process for you to test the benchmarker. And the results with the Fibonacci was that on around 1800 megabytes of memory, it was taking 600 milliseconds in build duration, because AWS will round up to the next 100 milliseconds. So 600 here, and by increasing to 2 gigabytes of memory, it will reduce to 500 milliseconds build duration. So it's a 17% reduction, which offsets to 5% savings at the end. And if we are running this function, I don't know, millions of times per day, it can be quite substantial savings. Another strategy we can use to save money on Lambda is to use the internal memory from Lambda container as a caching mechanism. So we all know that data loaded outside the Lambda handler sticks to the next invocations, so it remains in memory. So this can be used as a caching mechanism. So here's just a very, very simple basic example of a function that's receiving a request to get user data. It provides a username, and the system will get the user from the cache. And internally, the cache is storing information in a data mapping object. And then it checks for this local object first. If it's already in the cache, it returns immediately for the client. If it's not found in the cache, it just gets from the user's database, populates the cache, and then responds to the client. So this is a way for us to keep information that's constantly being used by Lambdas. But there are a few caveats to this strategy as well, because if you have a high concurrency application, your Lambda functions will have different caches, because you're going to have multiple containers serving multiple concurrent requests. So each container will have a different cache. So the latency experience for your clients might change depending on which container their requests hit. So it may lead to a not so homogeneous experience to your customers, your clients. So we also published an article here on this link that you can read more about this. It's important, as we mentioned at the beginning, to keep monitoring our infrastructure constantly for the cost performance. So we may evaluate our architecture today and it's performing well, but as things change and sometimes change really fast, we need to be constantly monitoring to check whether everything is on Rails. And one thing that Dashbird offers, for example, is alerting based on cost policies. So you can set, for example, when the invocation cost is above, let's say, $10 on some over the last 1 hour, it can send you an email or a Slack message alerting you, hey, this Lambda function is costing really much more than you were expecting. So it may be interesting for you to jump in and see what's going on. And it's very important that you set these policies, because you may be surprised at the end of the month with a very huge AWS bill, which is not really funny for us, not a fun experience for us. So it's very important to have a proactive alerting, and the AWS spending alerts are not as fine-grained as something that Dashbird offers. So we can have spending reports, but maybe not at the Lambda level, for example. And here you can select a group of Lambdas or a particular Lambda that you want to get alerted when it starts costing too much. And then moving to the database group of cost-saving opportunities. The DynamoDB on-demand capacity mode is it's amazing. I love this feature when they launched it. It's highly scalable, it's really resilient, but it can be quite expensive, up to 7 times more expensive than the provisioned capacity mode. To be fair, in some cases where demand is usually low, most of the time, but it experiences sporadic spikes in demand in a few moments of the day, the on-demand capacity mode can actually be cheaper than the provisioned capacity mode in practice, because with provision, we end up provisioning more than we actually need. So it may lead to wasted resources allocated throughout the rest of the day because of those spikes. And one thing to improve scalability in the provisioned mode that could be a lot cheaper in many use cases is to set the auto-scaling. It works relatively well for slow-paced variations. So we know that it lags behind when the demand starts to scale up very quickly, and it may lead to throttled requests on your DynamoDB table. And for read-intensive tables, we could use the DAX cache that's offered by AWS. The downside of DynamoDB DAX is that it's charged on an hourly basis, not per usage, and it can be quite expensive as well. So a very small instance, for example, that costs $58 per month, the T2 medium, it's a cost that is equivalent to more than 200 million read operations in the on-demand mode. So you really need to be running on a high throughput table to be able to reap benefits from DynamoDB DAX. But if that's your case and you are read intensive, the DAX can be a really good way for you to save money on DynamoDB operations and actually reduce latency because the cache is a lot faster than the DynamoDB table. Then another strategy to improve scalability in the provision mode is to use SQS as a load leveler. This works for write-intensive jobs and for jobs that are tolerant to eventual consistency data model, which means that when we apply this pattern, data is not going to be updated immediately in the database. So whatever service is reading information from this table might get data that is not the most up-to-date. So instead of having a Lambda function directly connected to a DynamoDB table, which would create uncertainty over how much resources we need to allocate on the DynamoDB table in the provisioned mode, what we could do is have the initial Lambda function connected to an SQS queue, which is highly scalable and it's fully serverless. And then the queue can be polled by a secondary Lambda. And if we set a throttling limit to this second Lambda, we know exactly the peak demand that the DynamoDB table can get. So regardless of how much demand the first Lambda is getting, we know exactly how much demand, the maximum demand that the DynamoDB table is going to get, because the SQS queue is leveling the load for us and the throttling in the second Lambda as well. So it makes it a lot easier to allocate resources on the DynamoDB table in the provisioned mode. And lastly, we have the CQRS. It stands for Command Query Responsibility Segregation in materialized views. It's the idea is that sometimes the way we store information in our database does not match exactly how we need to read them. And it may lead to excessive read requests to get all the information and then organize the information in a Lambda function, for example, before presenting the data to the client. So it can increase latency overall for the application as well. So the CQRS is about creating a secondary storage of the same data set, but in a way that matches the read patterns. So just to give you an example, consider we need to serve requests for LinkedIn profiles, for example, LinkedIn profile view requests, someone accessing someone else's profile, and we need to get a bunch of information. So basic user data, name, the job title, picture, short bio, etc. We need to get a list of the latest posts, employment history, skills and endorsements, and a bunch of other stuff. And each of those data points might be stored as different items in the database. And each profile request is going to lead to multiple read operations on the downstream database table. So we need to make one request to get the user data, another request to get career information, another one for skills and endorsements, etc. And it can really, like, one profile view can lead to, I don't know, 5, 10, 20 database requests. So with a materialized view, what we do is to create a single item that contains everything we need to serve a profile view request. And then we can use DynamoDB streams, for example, and Lambda to keep the materialized view up to date. We can store this materialized view in another DynamoDB table, or perhaps on an S3 bucket, we can store JSON views of a profile. if it's public information, you can even put a CloudFront distribution in front of this S3 bucket and distribute information in a very fast and cheap way through CloudFront. And the three downsides of this strategy is that it's eventually consistent. So when we update information in the main DynamoDB table, it's going to take some time for the materialized view to get updated as well. Maybe, I don't know, 1 second, 2 seconds. In some cases, that might be a problem. It increases the writes. So whenever someone writes something to the main table, we need to write something else on the materialized view as well, either a DynamoDB table or an S3 bucket. So we really need to measure and benchmark our use case to see whether the savings on the read side is going to offset the higher costs on the write side. And there could be data mismatches as well. If we have a bug in the Lambda function that's responsible for updating the materialized view, for example, it's possible that we're going to keep providing information in the materialized view that's not really the most up-to-date, for example. So those were the ideas we wanted to share with you. Those are high-level ideas. It's very difficult for us to get deeper in those cost-saving opportunities without really knowing each details of the implementations. So it's very customized to each situation. We will be sharing more content in the next weeks about those cost-saving opportunities. So be sure to follow us on social media. And we're also hiring. So if you're looking for a very cool startup to work with, heavily based on serverless, check our hiring page.
Renato, we also have a question. Sorry, I can't, for some reason, start my video again, but we do have a question. So it's about your GitHub repository that calculates the optimal memory size for a function. And the question is it possible to use the benchmarker without changing the Lambda code? And how would you recommend performing the tests without executing production code? So the first part is it possible to use the benchmarker without changing the Lambda code?
The thing is, so the Lambda, your Lambda needs to reply with some information. Let me double check here on the repo. I think that your Lambda has to respond with a few information for it to be precise. Let's see, benchmarker. Avi, can you try to enable your video again?
Okay, now it works.
Okay, perfect. So let me see here, the benchmark, Lambda. We wrote an article actually about this a while ago. So I don't have everything. It's been published several months ago, this repo. So I don't have every details from the top of my mind right now. What I remember, it's Federico, right, that asked the question, Federico Dallari. Thanks for the question, by the way. From what I can recall right now is that due to some limitations in how we need to monitor this information to have an accurate evaluation of multiple requests, I needed to get some information from the downstream Lambda. So it was required to have a little bit of code changes. But from what I remember, it was quite simple to change, actually.
Mm-hmm. Yeah, so I think my kind of initial comment here would be as well that, you know, those types of benchmarking would probably come into play for some high volume Lambdas where actually the volume of invocations is so big that you would significantly benefit in the really kind of right memory configuration.
Yeah. What I would do is redeploy the Lambda with a different name. like just redeploy the same code, make a small change, redeploy it, and connect to the benchmarker to test different levels of memory. And then when you find the memory sweet spot, then you can make the changes in your main Lambda configuration. It should take very, very little time, but it only pays off when you have a really high throughput Lambda function.
Yeah. So the other part of the question, how do you perform the tests without executing the production code?
Yeah, that's the idea. Just what I would suggest is to redeploy the Lambda. So do not try this in your production environment, not even in a production AWS account, because it's going to generate a lot of requests, and it might consume your Lambda concurrency quota. So if your application is already running near to the concurrency limit, it may start making your Lambda to throttle some requests, maybe to your clients in production. So what I would suggest is to have a separate AWS account and redeploy the function with a different name perhaps, and test there in a more safe environment.
Yeah, also as a side note, kind of to add, is that you do want to run these tests at a high concurrency situation so that you would see what problems are exposed when you're actually at a really high scale. So your databases or downstream services might start acting differently at that point, and then that might expose like additional delays.
Yes, I just, your comments just helped me to remember why we needed to make changes to the downstream Lambda, and it was the cold start issue. So I needed to check whether the Lambda was in a cold start, and then I just throw out those data points because they would skew the results. So the benchmarker only considers requests that when Lambda was warm. So I need to get some information back from the Lambda to identify whether it's in a cold start or not.
Yep, that makes sense. I hope that answers your question, Federico. So we have another question. Can Dashbird do tracing of serverless applications? The short answer is yes. We rely on AWS X-Ray to collect the data. So, and then that shows you the profile of the execution and what services an execution was talking to. We've made a fundamental choice here as well to not instrument our code or Lambda function code with our agents. Rather, we choose to centralize the data that is available for all cloud services, or at least the serverless spectrum of AWS, and rely on X-Ray, CloudWatch data, logs, metrics, tracing, and configuration data, and to show that as best as we can and extract value from that to not cause any performance issues. But on the other hand, the choice is that we see actually like a large increase in the usage of other managed services besides Lambda functions, and we see the future as kind of not just functions, but this whole kind of world that's going on next to Lambda functions. All right.
Also, if anyone has any suggestions as well, I don't know, anything you've done in the past that helped you to save money on AWS, if you'd like to share in the chat as well with everyone else that's connected, that would be great. Or if you'd like to send us later by email, perhaps we can, I don't know, publish an article about your experience on our blog. That would be great as well. So feel free to share your experiences.
Yeah. Yeah, so it seems we don't have any other questions. Thank you all for listening, and thanks Renato for giving us this presentation. I really enjoyed listening. I hope others did as well. And yeah, see you next time. I think it will be in a couple of weeks when we have another webinar. And yeah, wait for the slides and the presentation itself for the recording in your email. And yeah, thank you for listening.
Awesome. That was great. Bye-bye, everyone.
Bye.